Everyone thinks they know how heat works. Hot things radiate energy. Burn something, you get light. Simple, right? But at the end of 1899, physicists stood in front of a problem so brutal it threatened to collapse everything they thought they understood about reality. Classical physics said a heated oven should glow with infinite brightness and vaporize the universe. Obviously, that didn't happen. And the man who solved it? Max Planck never wanted to break physics. He hated the answer he found. What Planck discovered about heat wasn't just clever math. It was a crack in the foundation of the universe itself, and we're still living in the consequences. By the 1890s, industrial competition with Britain and the United States was brutal. The Germans needed an edge. They built the Physikalische Technische Reichsanstalt, the Imperial Institute of Physics and Technology, in Charlottenburg, a district of Berlin. Hermann von Helmholtz, one of the greatest physicists of the 19th century, became the founding director. The mission: establish measurement standards, develop precision instruments, and dominate the physics of light and electricity. Inside the institute by 1895, Wilhelm Wien and Otto Lummer constructed the first proper blackbody radiator, a cavity with a small opening. Heat the cavity, the radiation inside reaches equilibrium with the walls, the opening lets out a sample. That sample is blackbody radiation, as pure as you can get. By 1898, Lummer and Ferdinand Kurlbaum had developed electrically heated cavities reaching temperatures from minus 188 Celsius, using liquid air cooling all the way up to 1500 Celsius, later pushed to 1600. They built bolometers, sensitive thermometers using thin platinum strips, detecting infrared radiation. Ernst Pringsheim joined Lummer to map the spectrum across an enormous wavelength range. But nobody could derive what that law was. The experimental teams measured intensity versus wavelength at different temperatures. The curves all had the same shape. Intensity rises with decreasing wavelength, peaks, then drops off fast at shorter wavelengths. As temperature increases, the peak shifts to shorter wavelengths and the total intensity explodes. Wilhelm Wien tackled the problem theoretically in 1896. He derived a relationship from thermodynamics and electrodynamics. His formula: intensity proportional to frequency cubed times e to the minus h nu over kt, where nu is frequency, t is temperature, and h and k are constants. At high frequencies, short wavelengths, Wien's distribution law fit the data beautifully. It explained why hot objects glow different colors: red hot iron at 900 Kelvin, orange at 1100, yellow-white at 1500. Wien won the Nobel Prize in 1911 for this work. But there was a problem brewing. At low frequencies, long wavelengths, Wien's law predicted intensity should drop off exponentially fast. Experiments in the conventional infrared, 1 to 8 microns, matched Wien. But push further into the far infrared, 12 microns, 30 microns, 50 microns, and the curve started bending wrong. The data sat higher than Wien predicted. Not a lot at first. Small deviations, measurement error maybe. Rock salt and fluorite crystals reflect specific wavelengths strongly. Use that property to filter out a narrow band, measure its intensity. Clean measurement, hard to dispute. By September 1900, the deviations were undeniable. At 51 microns, the intensity increased linearly with temperature, not exponentially as Wien said. This matched what Lord Rayleigh in England had predicted from pure classical reasoning. Rayleigh's law: intensity proportional to temperature over wavelength to the fourth. At long wavelengths, low frequencies, classical equipartition theorem said every mode should have energy, kT. Rayleigh showed the number of modes goes as frequency squared. Combine them, you get Rayleigh's formula. It matched the far infrared data. But at short wavelengths, Rayleigh's law exploded. Integrate over all frequencies, and you get infinite total energy. The ultraviolet catastrophe, named later by Paul Ehrenfest in 1911, but the problem was real. Classical physics couldn't explain the full spectrum. Wien's law worked at high frequencies, but failed at low. Rayleigh's law worked at low frequencies, but failed catastrophically at high. Two separate laws, neither universal. Enter Max Planck. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the Wikipedia article on Planck's law updated 1 week ago in December 2025, and from Physics World's April 2025 article titled Max Planck the Reluctant Revolutionary by Helge Krag, which provides detailed analysis of Planck's actual beliefs versus later mythologies. These aren't generic sources. Krag's work dismantles common physics textbook myths about what Planck actually thought he was doing in 1900. Now back to the information. They'd pushed into the far infrared, 51 microns wavelength, using rock salt reflections to filter the spectrum. The data was clean, and Wien's law was wrong. Not close, wrong. At long wavelengths, the radiation intensity increased linearly with temperature, exactly as Lord Rayleigh had predicted in a 2-page paper from June 1900. Wien's formula said it should drop exponentially. The guests left. Planck sat down. He didn't sleep. By the next morning, he'd written a new formula on a postcard and mailed it to Rubens. Rubens got it Monday morning, tested it against the data. It fit perfectly, at every wavelength, every temperature. The experimental teams at the PTR couldn't find a deviation. On October 19, 1900, at the German Physical Society meeting in Berlin, Kurlbaum presented the new infrared data. Immediately after, Planck stood up and presented his formula. It had 2 universal constants, Boltzmann's constant and a new constant he labeled h. Nobody knew what h meant yet. Planck didn't either. He just knew it made the math work. He studied in Munich and Berlin under Gustav Kirchhoff, the man who'd posed the black-body problem decades earlier. Planck's early work focused on thermodynamics, particularly entropy and irreversibility. He believed passionately in absolute truths, universal laws that didn't depend on human observation or probability. This put him at odds with Ludwig Boltzmann's statistical mechanics. Boltzmann argued that the second law of thermodynamics, the law that entropy always increases, was statistical. It held on average, not absolutely. There was a tiny but non-zero probability that entropy could decrease, that heat could flow from cold to hot spontaneously. Planck rejected this. He wanted strict determinism, no probabilities, no exceptions. He spent years trying to prove the second law was absolute, not statistical. He failed. Nature doesn't care what you want. If he could derive the universal radiation law from pure thermodynamic principles, it would vindicate his belief in absolute laws. He treated the cavity as filled with electromagnetic oscillators, charged particles in the walls, vibrating at all possible frequencies. The oscillators exchange energy with the radiation field. At thermal equilibrium, the energy distribution should be fixed by temperature alone. Planck developed a thermodynamic relationship for entropy in terms of energy. He applied Maxwell's electromagnetic theory. He derived Wien's law in 1899 and published a paper claiming it was the universal function Kirchhoff had predicted. Then, the new data came in. You derive from first principles, then compare to experiment. Planck had done it backward. For the next 2 months, he tore into the problem. He tried everything. Maxwell's electromagnetic wave equations, dead end, continuous thermodynamics, couldn't reconcile. Planck was stuck because he'd built his career on absolutes. He believed the second law of thermodynamics was a strict deterministic law, not probabilistic. He didn't believe in atoms. He thought Ludwig Boltzmann's statistical mechanics, which treated entropy as a matter of probability and molecular arrangements, was speculative nonsense. Boltzmann had introduced discrete energy states in 1877 purely as a mathematical trick, a way to count configurations before letting the size of the energy packets shrink to zero. Planck hated that approach. It was messy. It relied on probability. It assumed atoms existed, which Planck doubted. But in December 1900, Planck was out of options. To make Boltzmann's approach work for his black-body formula, Planck couldn't let the energy element shrink to zero the way Boltzmann had. The element had to stay finite. He divided the total energy of his oscillators into chunks, each chunk proportional to the frequency times his new constant h. Energy could only be emitted or absorbed in integer multiples of h times frequency. 1 chunk, 2 chunks, 3. Never 1.5 chunks. This was quantization, though Planck didn't call it that yet. He called h the elementary quantum of action. Its value from the blackbody data, 6.55 times 10 to the minus 34 joule seconds. That's within 1.2% of the modern value of 6.62607015 times 10 to the minus 34. Planck also calculated Boltzmann's constant to high precision for the first time, another number we still use. That's a combinatorial problem. The number of ways is p plus n minus 1 factorial divided by p factorial times n minus 1 factorial. Boltzmann let epsilon go to 0 as p goes to infinity, keeping u fixed, continuous energy. But Planck stopped. He set epsilon equal to h nu, fixed, finite, non-zero. With that choice, the number of microstates for energy u is n plus u over h nu minus 1 factorial, divided by u over h nu factorial times n minus 1 factorial. Entropy S equals k natural log of that number. Use Stirling's approximation for large factorials. Work through the algebra. You get entropy as a function of energy. Invert it. Energy as a function of entropy. The derivative du over ds at constant volume equals temperature T. Solve for average energy per oscillator. You get u over n equals h, nu divided by e to the h nu over kt minus 1. That's the quantized oscillator energy. Multiply by the number of modes per frequency interval from classical electromagnetism, 8 pi nu squared over c cubed. You get Planck's spectral energy density, 8 pi h nu cubed over c cubed times 1 over e to the h nu over kt minus 1. That's the Planck distribution. Convert from frequency to wavelength using nu equals ce over lambda. You get the wavelength form, 8 pi hc over lambda to the fifth times 1 over e to the hc over lambda kt minus 1. This formula interpolates perfectly between Wien at short wavelengths and Rayleigh Jeans at long wavelengths. The constant h is the crossover scale. When hnu is much greater than kt, the exponential dominates and you recover Wien. When h nu is much less than kt, expand the exponential to first order, ai to the x approximately 1 plus x, and you recover Rayleigh Jeans. Planck's formula unified both limits. It was the universal law Kirchhoff had demanded 40 years earlier. Planck saw the quantum as a quirk of matter, not radiation. He hoped someone would eventually figure out how to derive his law without this weird, discrete energy assumption. He didn't celebrate. He didn't think he'd started a revolution. The December presentation was met with polite interest and immediate silence. Nobody rioted. Nobody declared the birth of quantum theory. Physicists noted the formula fit the data beautifully, thanked Planck, and moved on. For 5 years, almost no one took the energy quantization seriously. Planck himself kept trying to derive the law differently, hoping to eliminate the discrete energy assumption. In 1906, he published lectures on thermal radiation that argued for a continuum theory without mentioning discrete oscillator energies. If he'd seen the light in 1900, why backtrack 6 years later? The answer, he hadn't seen the light. He'd found a formula that worked and used a mathematical method he didn't trust to justify it. Times 1 over e to the hc over wavelength, times Boltzmann's constant times temperature minus 1. At short wavelengths, high frequencies, the exponential term dominates and the intensity drops fast. This matches Wien's law in that region. At long wavelengths, low frequencies, you can expand the exponential and the formula reduces to 8 p Boltzmann's constant times temperature divided by wavelength to the fourth. That's the Rayleigh Jeans law. Planck's equation was the bridge. It worked everywhere because it included both behaviors and smoothly transitioned between them. The constant h set the scale where the transition happened. For everyday temperatures and wavelengths, h is absurdly tiny. That's why classical physics worked for centuries. But at atomic scales, h is everything. Here's the problem. It didn't exist in 1900. The name was coined by Paul Ehrenfest in 1911, more than a decade after Planck's work. The catastrophe refers to the Rayleigh Jeans law predicting infinite energy at high frequencies if you integrate over all wavelengths. But Rayleigh published his law in June 1900, after Wien's law had already been shown to fail at low frequencies. Rayleigh knew his law failed at high frequencies. He said so explicitly. He thought equipartition might apply only to low-frequency modes. The narrative that Planck was heroically solving the ultraviolet catastrophe is a later myth. What Planck was solving in October 1900 was Wien's law failing in the infrared. The catastrophe became important later when Einstein and others used it to argue that classical physics was fundamentally broken, not just approximately wrong. But in 1900, not on Planck's radar. This is confirmed in the April 2025 Physics World article by Krag, and in multiple historical analyses by Thomas Kuhn from the 1970s. His big contribution was statistical mechanics, the idea that thermodynamic properties like temperature and entropy emerge from the statistical behavior of vast numbers of atoms and molecules. In 1877, he wrote a paper deriving entropy from the number of ways you could arrange particles in different energy states. The formula S equals k times natural log of omega, where omega is the number of microstates, became the definition of entropy. But here's the tragedy. Boltzmann fought for decades against physicists who didn't believe atoms were real. Ernst Mach, one of his colleagues in Vienna, was a vocal opponent. Boltzmann suffered from depression and poor eyesight. In September 1906, while on vacation in Duino, Italy, he hanged himself. He didn't leave a note. His daughter found him. 4 months earlier, his doctor had diagnosed neurasthenia and forbidden him from scientific work. Boltzmann died thinking his ideas had failed. But in 1905, Albert Einstein published his work on Brownian motion, using statistical mechanics to predict observable effects of molecular collisions. Between 1908 and 1909, Jean-Baptiste Perrin confirmed Einstein's predictions with experiments on colloidal particles, directly measuring Avogadro's number and Boltzmann's constant. The atomic hypothesis was proven. Boltzmann's statistical mechanics was vindicated, just 2 years too late. Max Planck later wrote, The logarithmic connection between entropy and probability was first stated by L. Boltzmann in his kinetic theory of gases. The formula is carved on Boltzmann's tombstone in Vienna. Planck published his full derivation in early 1901 in Annalen der Physik. The title, On the Law of Distribution of Energy in the Normal Spectrum. It laid out the mathematics, the assumptions, the constants. And then the physics community mostly ignored it. Why? Because quantization looked like a mathematical artifact. Planck himself called it a purely formal assumption. He admitted he didn't think much about it. If the man who discovered it wasn't sure it was real, why should anyone else be? The formula worked, sure, but working and being fundamental are different things. Classical physics had produced countless useful formulas by approximation. Maybe this was just another approximation waiting for a proper derivation. While working as a patent clerk in Bern, Switzerland, Einstein published 4 groundbreaking papers in Annalen der Physik, one on Brownian motion proving atoms, one on special relativity, one deriving E equals mc squared, and one on light quanta, the photoelectric effect. That last one changed everything for Planck's quantum. Einstein read Planck's work and took it further. Planck had quantized the energy of material oscillators. Einstein quantized light itself. In his March 1905 paper on a heuristic viewpoint concerning the production and transformation of light, Einstein argued that electromagnetic radiation doesn't just interact with matter in discrete chunks. Radiation is discrete chunks. Light propagates through space as localized particles carrying energy E equals hnu, where nu is frequency. Einstein called them light quanta. Later, they'd be named photons. This was radical beyond radical. It contradicted Maxwell's wave equations, which had been physics gospel since the 1860s. But Einstein used it to explain the photoelectric effect. When you shine light on a metal, electrons are ejected, but only if the light frequency exceeds a threshold. Increase intensity, more electrons, same energy. Increase frequency, same number of electrons, higher energy. Classical wave theory predicted intensity should matter for electron energy. It didn't. Energy depended only on frequency. Einstein's quantum explanation fit perfectly. One photon hits one electron, transfers all its energy. Electron escapes if the photon energy exceeds the metal's work function. The leftover energy becomes kinetic energy of the electron. Simple, testable, correct. Planck himself rejected them for years. At the first Solvay conference in 1911 devoted to radiation and quanta, Planck still argued for continuous radiation. He thought Einstein had gone too far. Even Planck, the man who started quantum theory accidentally, thought quantizing light was absurd. It took experimental proof. In 1916, Robert Millikan, who had spent a decade trying to disprove Einstein, finally published experiments that confirmed the photoelectric equation exactly. Millikan used ultraviolet light on sodium, potassium, and lithium surfaces. He measured the stopping potential needed to prevent electron emission as a function of light frequency. The relationship was perfectly linear. Slope, h divided by electron charge. Intercept, negative work function divided by electron charge. The data gave h equals 6.56 times 10 to the minus 34 joule seconds, agreeing with Planck's blackbody value to better than 1%. Millikan got a Nobel Prize in 1923 partly for this work. Einstein got his Nobel in 1921, awarded in 1922, specifically for the photoelectric effect, not relativity. The committee cited his discovery of the law of the photoelectric effect. That's how important it was. The committee wanted experimental confirmation before rewarding relativity, and that didn't come until Ives and Stilwell in 1938, decades later. By then, quantum mechanics was already rewriting textbooks. Some scattered rays had the same wavelength as the incident beam, but some had longer wavelengths. The shift depended on scattering angle. Compton treated the X-rays as particles colliding with electrons like billiard balls. Conservation of energy and momentum gave him an equation relating wavelength shift to angle. Delta lambda equals h divided by electron mass, times c times 1 minus cosine theta, where theta is the scattering angle. For scattering at 90 degrees, delta lambda equals 2.43 times 10 to the minus 12 meters. That's the Compton wavelength of the electron. The data matched the formula perfectly at all angles. Light quanta carried momentum equal to h divided by wavelength. They were particles with definite energy and momentum, but they also had wavelengths and frequencies. Wave-particle duality wasn't philosophy anymore, it was measurement. Repeat the experiment with lower energy light, visible photons. The effect becomes unmeasurable because photon momentum is too small to kick electrons significantly. But at X-ray energies, 15 to 20 kilo electron volts, photon momentum is comparable to electron momentum. The collisions are billiard ball clear. Compton won the Nobel in 1927 for this work. The photon was real. Light is both wave and particle depending on how you measure it. Which aspect you see depends on the experiment. No contradiction. Just complementarity, as Niels Bohr would later frame it. When an electron jumps between levels, it emits or absorbs a photon with energy equal to the difference. This explained atomic spectra, the discrete wavelengths atoms emit when excited. Hydrogen's spectrum, which had been measured since the mid-1800s, fit Bohr's formula exactly. The Balmer series, visible lines at 656, 486, 434, and 410 nanometers. The Lyman series in ultraviolet, the Paschen series in infrared, every line corresponded to an electron transition. Energy level n equals 1 to n equals 2. 10.2 electron volts, 122 nanometer photon, n equals 2 to n equals 3. 1.89 electron volts, 656 nanometers, the red hydrogen alpha line. The formula worked. Bohr's model wasn't complete. It couldn't handle multi-electron atoms or explain why some transitions were brighter than others, but it was a start. It proved quantization of angular momentum. Electron orbits can't be arbitrary circles, only specific radii allowed, where angular momentum equals integer times h divided by 2 pi. Specific heat. Classical theory predicted every solid should have the same specific heat. 3 times Boltzmann's constant per atom, the Dulong-Petit law. It worked at room temperature for most materials, but at low temperatures, specific heats dropped. A diamond at 50 Kelvin has specific heat far below the classical prediction. Einstein modeled a solid as atoms, vibrating in 3 dimensions, each atom a quantum oscillator with energy n watt nu, where n is an integer. At high temperatures, lots of energy quanta are excited, specific heat approaches the classical value. At low temperatures, fewer quanta are excited, specific heat drops. The model qualitatively explained the data. Peter Debye improved it in 1912 by accounting for different vibration frequencies in the solid, creating the Debye model. That model is still used today to calculate thermal properties of materials. Again, Planck's H was essential. Without quantization of vibration energy, specific heat wouldn't decrease at low temperature. Classical equipartition demanded constant specific heat. Nature said no. An electron moving at 1 million meters per second has momentum about 9 times 10 to the minus 25 kilogram meters per second. Wavelength, h over p, equals 7.3 times 10 to the minus 10 meters, comparable to atomic spacing in crystals. That means electrons should diffract off crystal lattices just like X-rays do. In 1927, Clinton Davison and Lester Germer at Bell Labs in New Jersey fired slow. Electrons at a nickel crystal. They saw diffraction peaks at specific angles, exactly as predicted by de Broglie's wavelength formula. Electrons were waves. George Paget Thomson, son of J. Thomson, who discovered the electron, did independent diffraction experiments in Scotland the same year. Davison and Thomson shared the Nobel Prize in 1937. J. Thomson got the Nobel in 1897 for showing electrons are particles. His son got the Nobel for showing electrons are waves. Physics has a sense of irony. For a free particle, the wave function is a plane wave with wavelength h over momentum. For a particle in a potential, the wave function satisfies Schrödinger's equation, minus h squared over 8. Pi squared m times the second spatial derivative plus potential energy times wave function equals IH over 2 pi times time derivative. Solve this for an electron in a hydrogen atom. You get quantized energy levels matching Bohr's formula. But now you also get the shapes of orbitals, the probability clouds where electrons live. S orbitals, spherical, p orbitals, dumbbell-shaped, d orbitals, cloverleaf. Quantum numbers n, l, m fall out naturally. No ad hoc assumptions about allowed orbits. Just solve the wave equation. Chemistry became applied quantum mechanics. Why carbon bonds to 4 hydrogens, why nitrogen is triple bonded, why metals conduct. All explained by electron wave functions. The periodic table's structure reflects quantum mechanics. Shells and subshells are energy levels and angular momentum states. Every element's chemistry follows from Schrödinger's equation plus Pauli's exclusion principle, which says no 2 electrons can be in the same quantum state. Wolfgang Pauli introduced that in 1925. Nobel Prize, 1945. In 1927, Werner Heisenberg formulated his uncertainty principle. You can't simultaneously know a particle's position and momentum beyond a limit set by Planck's constant. Delta x times delta p is at least h divided by 4 pi. Measure position precisely, momentum becomes uncertain. Measure momentum precisely, position becomes uncertain. It's not a measurement limitation, it's fundamental. A particle doesn't have a definite position and momentum simultaneously. The uncertainty is baked into the wave function. Heisenberg derived it from the commutation relation of position and momentum operators. Quantum mechanics became a complete framework, states described by wave functions, observables represented by operators. Measurement collapses the wave function to an eigenstate. Time evolution governed by Schrödinger's equation. And all of it traced back to December 14, 1900, when Planck stood in front of the German Physical Society and introduced H. Law published June 30th, 2023, and from multiple peer-reviewed papers on ArcSev, including Quant PH 0010008, titled How Planck Discovered His Radiation Formula, from October 2000. These sources dive deep into the actual timeline of Planck's thought process, separating legend from documented fact. Now back to the information. Its dimension is energy multiplied by time, which physicists call action. In classical mechanics, action is the integral of momentum times distance over a particle's path. Minimizing action gives you the equations of motion. It's a deep principle. Planck's constant sets the minimum quantum of action in nature. Any process that changes a system's action must change it by at least h. You can't have half h. This is why macroscopic objects don't show quantum effects. A baseball has action trillions of times larger than h. Quantization is invisible. But an electron orbiting an atom? Its action is on the order of h. Quantization dominates. The orbit can't be arbitrary. It must be an integer multiple of h divided by 2 pi. That's Bohr's quantization condition. Planck's constant appears everywhere in quantum mechanics because it's the unit of action, the conversion factor between the particle description and the wave description. De Broglie's wavelength, h over momentum. Heisenberg's uncertainty, position. Uncertainty times momentum. Uncertainty is at least ah divided by 4 pi, Schrödinger's equation. The time derivative of the wave function equals h divided by 2 pi. I times the Hamiltonian acting on the wave function. Every equation, h is there. It's the scale of quantum reality. The modern value, defined exactly since May 2019 when the kilogram was redefined. 6.62607015 times 10 to the minus 34 joule seconds. No error bars. It's a defined constant now, part of how we construct the SI unit system. The citation. In recognition of the services he rendered to the advancement of physics by his discovery of energy quanta. Planck was 60 years old. By then, quantum mechanics was mainstream, and Planck had accepted, reluctantly, that his quantum was fundamental. But his journey there was painful. He'd spent the first decade of the 1900s trying to eliminate the quantum. He'd argued with Einstein. He'd published papers suggesting ways to restore continuity. He failed. Nature is quantized. The evidence kept piling up. Atomic spectra, specific heat of solids, photoelectric effect, Compton scattering, all of it demanded quanta. Planck finally surrendered. In his later writings, he acknowledged that the quantum was not a trick. It was real, and it was absolute. For a man who'd spent his career seeking absolute laws of nature, finding one that smashed his favorite assumptions must have been torture. But he adapted. By 1918, Planck was recognized as the founder of quantum theory, even though he'd never intended to found anything. Plug that into Planck's law. Peak emission occurs at roughly 500 nanometers wavelength, green light, right in the middle of the human visible spectrum. Not a coincidence. Our eyes evolved under sunlight. We're most sensitive to the wavelengths the sun emits most strongly. But peak per wavelength and peak per frequency are different because wavelength and frequency intervals don't map 1-to-1. Peak per frequency is at 343 terahertz, corresponding to 883 nanometers near infrared. About half the sun's radiation is shorter than 710 nanometers, roughly the red edge of human vision. About 12% is ultraviolet, wavelengths shorter than 400 nanometers. The sun is a nearly perfect blackbody. Wien's displacement law, derived from Planck's formula, says peak wavelength times temperature equals 2.9 times 10 to the minus 3 meter Kelvin. For the sun, 500 times 10 to the minus 9 meters times 5778 Kelvin equals 2.889 times 10 to the minus 3, spot on. Now take a wood fire, 1500 Kelvin, peak at 2000 nanometers, deep infrared. 98% of its radiation is longer than 1000 nanometers, barely any visible light. That's why a campfire warms you but doesn't illuminate much. Human skin, 300 Kelvin, peak at 10 microns, far infrared. You're glowing right now. Infrared cameras see you easily. Heat-seeking missiles lock onto this emission. Every object above absolute zero radiates according to Planck's law. The hotter it is, the shorter the peak wavelength, the more total power. Power increases as temperature to the fourth. Stefan Boltzmann law derived from integrating Planck's formula. An object at 600 Kelvin radiates 16 times more power per square meter than one at 300 Kelvin. This is why stars are so luminous. Surface area for area. A star at 10,000 Kelvin puts out 10,000 to the fourth, equals 10 to the 16 times more power than your skin. Ratios like that explain why the universe looks the way it does. Transistors wouldn't have been invented in 1947. No transistors, no computers, no internet, no smartphones. Modern chemistry relies on quantum mechanics to predict molecular bonds. Drug design uses quantum calculations. Solar cells depend on the photoelectric effect. Lasers are stimulated emission, a quantum phenomenon Einstein described in 1916. MRI machines exploit quantum spin states. Quantum mechanics isn't just academic, it's the foundation of the modern world. And it started because Planck needed to fit a curve. Planck ignored the advice and enrolled in 1874. Good thing. If he'd listened, we'd be missing one of the most important constants in physics and one of the strangest revolutions in human thought. Planck was methodical, careful, obsessed with finding ultimate truths. His doctoral dissertation dealt with the second law of thermodynamics. He believed in deterministic absolute laws, not probabilistic statistical ones. And then he accidentally birthed quantum mechanics, which at its core is irreducibly probabilistic. You can't predict exactly when a radioactive atom will decay. You can only give odds. Quantum mechanics says the universe runs on dice rolls at the fundamental level. Einstein hated this. God does not play dice with the universe, he said. Bohr replied, Einstein, stop telling God what to do. The debate raged for decades. Planck, stuck in the middle, found himself father to a theory he never fully embraced. He accepted quanta were real, but the deeper implications, the collapse of determinism, the intrusion of randomness into the bedrock of physics, he struggled with that until the end. His daughter Greta died in childbirth in 1917. Her twin sister Emma married Greta's widowed husband and also died in childbirth in 1919. His second son Erwin was executed by the Nazis in 1945 for his role in the July 20th plot to assassinate Hitler. Planck outlived most of his children. He died in October 1947 in Göttingen, Germany, 89 years old, after Allied bombs had destroyed his house and much of his work. The Max Planck Society, Germany's premier research organization, was renamed in his honor after World War II. Before the war, it was the Kaiser Wilhelm Society. The rebrand was deliberate. Distance from the Nazi era. Honor a man who represented the best of German science. Planck was never a Nazi. He opposed them privately and tried to use his status to protect Jewish colleagues. It didn't work. He watched Germany collapse around him and his family torn apart. That single wavelength, that one data point deviating from Wien's law, forced Planck to invent quantum mechanics. If Rubens had stopped at shorter wavelengths, if the PTR hadn't pushed their technology into the far infrared, Wien's law might have stood for years. Someone else might have found the quantum eventually, but maybe not in 1900, maybe not Planck. The whole trajectory of 20th century physics pivoted on one dinner conversation, one wavelength, one postcard mailed Monday morning, October 8th, 1900. Rubens opened his mail, saw the formula, tested it. Fit perfect. Quantum mechanics was born in a postcard from a theorist to an experimentalist before either of them realized what they'd found. Planck's constant had entered the world. 6.63 times 10 to the minus 34. The number that sets the scale of everything that matters.